Hi, good evening students. Today we are going to discuss the topic differentiability. In this section, we have to define the operation differentiation on a real valued function f of x. Let us consider the function y equal to f of x be a real valued function. That is, x belongs to set of real number. Let c be any point in the domain of f and h be a small real number. Then the derivative of f at c is defined by limit h tends to 0 f of c plus h minus f of c divided by h. What is this meaning? Here, first we can consider a real valued function f of x. Then next we have to apply an operation differentiation. We will get the result that is denoted by f dash of x. It is called the derivative of the function f of x. Here, f of x can be written as y equal to f of x be a real valued function. Therefore, the derivative of f of x is denoted by f dash of x. It is also denoted by dy by dx. That is derivative of the function y with respect to x. It is also denoted by f dash of x. And it is again denoted by y dash or y1. That is, the derivative can be expressed f dash of x dy by dx, y dash or y1. Now here, how can we define the derivative of the function f of x? Here, derivative means the rate of change of increment or decrement of the function. That is, let us consider the function f of x. Let c be any point on the function. Then we can define at x equal to c, it can be defined as f of c. That is, this function can be changed into f of c. Next, we can consider a smallest increment of this function. That is, let us consider a smallest increment h. Therefore, the function can be changed into f of c plus h. That is, f of c can be changed into f of c plus h. It is the smallest increment on the function. That means the right of f of x or the right of f of c, there will be a smallest increment. Therefore, the function can be changed into f of c plus h. Then here we have to define the rate of change of this increment. That means this smallest region is denoted by the f dash of c. In the right side of f of c, we can consider the increment of the function. And in the left side of f of c, we can consider the decrement of the function. Here, it is an increment. That is smallest increment. Therefore, f of c can be changed into f of c plus h. This is denoted by f of c plus h. Next, we can consider this smallest increment. That means f of c plus h minus f of c. We will get this smallest increment. At the same time, the rate of increment, here h is the rate of increment, therefore it can be dividing throughout by h. Then limit h tends to 0, f of c plus h minus f of c divided by h. This is denoted by the smallest increment of this function. That is, this is the derivative of the function. Therefore, it can be denoted by limit h tends to 0, f of c plus h minus f of c divided by h. That is, f dash of c equal to what? Limit h tends to 0, f of c plus h minus f of c divided by h. That is the rate of increment of the function. It is denoted by the derivative of the function. That is, f dash of c can be written as limit h tends to 0, f of c plus h minus f of c divided by h. That is, this is the right side of the function. That is, it can be denoted by the right hand derivative. That is, it is smallest increment on the right of f of c. Next, we can consider the smallest decrement. That means this side. Then how can we consider smallest decrement? It is minus h. Therefore, the function can be changed into what? It can be changed into f of c minus h. That is smallest decrement of the function. That is this smallest region. That is, this region is denoted the derivative of the function. It is the left side of f of c. That means it is left hand derivatives. This one is right hand derivatives. Then next we can consider the left side of f of c. We will get left hand derivative. How can we consider it is smallest decrement of f of c? That is, how can we find out this region? That is, it is equal to, then f dash of c is again denoted by limit h tends to 0, f of c minus h minus f of c, then this distance, f of c minus h, this is denoted by this region, f of c minus h, then minus f of c. Therefore, we will get this smallest region. That is divided by, here, the left side of f of c. The function is f of c minus h minus f of c. That is, here the function, total function is f of c minus h, then minus f of c divided by, here the smallest decrement, it is minus h. That is, this is the left-hand derivative of the function f of x. That is, it is left-hand derivative. Next, we have to discuss algebra of derivatives and derivative of some standard functions. Let us consider u and v are two differentiable functions. The differentiable function means the derivative of this function will be existing. That is, it has derivative. Let u and v are two differentiable functions. That means that is u dash and v dash are exist. Then the first algebra of the derivative, first one, u plus v whole dash equal to u dash plus v dash. Second one, u minus v whole dash equal to u dash minus v dash. Then third one, uv whole dash equal to u into v dash plus v into u dash. U into v whole dash equal to u v dash plus v u dash. That is first function into derivative of second plus second function into derivative of first. Then next one, u by v whole dash equal to v into u dash minus u into v dash divided by v square. That is, the function is of the form u by v. Therefore, the derivative of u by v, that is u by v whole dash equal to v into denominator into derivative of numerator u dash minus numerator into u into derivative of denominator v dash divided by denominator square. That is, this is the quotient rule and this is the product rule. That is, uv whole dash equal to u into v dash plus v into u dash. This is product rule. Then the function is of the form u by v. That is, u by v whole dash equal to v into u dash minus u into v dash divided by v square. This is the quotient rule. Let k be any real number or k be any constant. Therefore, k into u whole dash equal to k u dash, where k is a constant. That is, where k is a real number. Therefore, k u whole dash equal to k into u dash. Here, k is a constant value. Then next we can consider derivative of some standard function. Let us consider a constant function. F of x is a constant, therefore the derivative is 0. And f of x equal to x, the derivative is 1. And f of x equal to x raised to n, derivative is n x raised to n minus 1. And then f of x equal to 1 by x, derivative is minus 1 by x square. F of x equal to root x, derivative is 1 by 2 root x. Then next consider the trigonometric function. F of x equal to sin x, derivative is cos x. Then f of x equal to cos x, derivative is minus sin x. Then f of x equal to tan x, derivative is sec square x. Then f of x equal to sec x, derivative is tan x sec x. Then f of x equal to cot x, derivative is minus cosec square x. Then f of x equal to cosec x, cosec x, derivative is minus cot x cosec x. This is your previous knowledge. Next, consider the theorem. F has derivative at x equal to c, then f is continuous at x equal to c. How can we prove this theorem? First, the given condition, f has derivative at x equal to c. Therefore, we can define f dash of c. Here, f dash of c is equal to what? Limit h tends to 0, f of c plus h minus f of c divided by h by the definition of differentiability. Then next, that is f dash of c exists at x equal to c. It is a given condition. Next, we can consider f of c plus h can be written as f of c plus f of c plus h minus f of c. That is, f of c plus h can be written as f of c plus f of c plus h minus f of c. That means it has no change. We have to add f of c and subtract f of c. The both side of f of c plus h, it has no change. Then next, we can consider it is equal to f of c plus f of c plus h minus f of c divided by h and multiplied by h. That is, we have to multiply the second term by h and also divide it by h. We have to rearranging the second term f of c plus h minus f of c divided by h into h. Next, we can consider limit h tends to 0 f of c plus h. It is equal to limit h tends to 0 f of c plus limit of the function f of c plus h minus f of c divided by h into h. That is, we have to apply limit on this function. That implies limit h tends to 0 f of c. F of c is a constant value. Therefore, we can take it as outside. Therefore, f of c plus, next we can consider limit h tends to 0 f of c plus h minus f of c divided by h, then multiplied by h. Here, limit h tends to 0, f of c plus h minus f of c divided by h. What is this? This is f dash of c. F has the derivative at x equal to c. That is why here limit h tends to 0, f of c plus h minus f of c divided by h is f dash of c. That implies then it will be equal to what? Limit h tends to 0, f of c plus h equal to, here the right side, it is f of c plus limit h tends to 0, f of c plus h minus f of c divided by h. It is f dash of c. Then limit h tends to 0, h, the value will be 0. That implies f of c plus 0, that's equal to f of c. Therefore, limit h tends to 0, f of c plus h is equal to f of c. That means f is continuous at x equal to c. That is here, f has derivative at x equal to c means f is differentiable at x equal to c. That is, this function is differentiable and it will be also equal to continuous function. That is, the differentiable function is always continuous. Next question. Consider the function f of x equal to mod x is differentiable on minus infinity 0 and 0 infinity, but it has no derivative at x equal to 0. Prove it. Here, the given function is f of x equal to mod x. First, we have to find out the given function f of x equal to mod x is differentiable on the interval minus infinity 0 and 0 infinity. By the definition of differentiability, we can define f dash of x. How can we define f dash of x equal to limit h tends to 0, f of x plus h minus f of x divided by h. The given function is f of x equal to mod x. First, we can consider the given function is differentiable or not. Let proof, let x belongs to minus infinity 0. Then f of x is what? Here f of x is mod x, that is x belongs to minus infinity 0. Therefore, f of x is minus x. Then, by the definition of differentiability, f dash of x can be written as f dash of x equal to limit h tends to 0, f of x plus h minus f of x divided by h. Here, the given function is what? F of x equal to mod x. Then here, x belongs to minus infinity 0, f of x is minus x. Therefore, substituting here, that's equal to limit h tends to 0, minus of x plus h minus of minus x divided by h. Then minus of x plus h, it is equal to limit h tends to 0, minus x minus h, then minus of minus, that is plus x divided by h. Then here minus x plus x cancel. That implies limit h tends to 0, minus h divided by h. That is equal to limit h tends to 0, minus h by h, that is equal to minus 1. Then limit h tends to 0, minus 1, it is equal to minus 1. That is, here f dash of x exists on the interval minus infinity 0. Here f dash of x is equal to minus 1. That is, the function y equal to f of x, it is equal to mod x. Therefore, derivative is denoted by y dash or f dash of x. Now here, y dash or f dash of x will be equal to what? Minus 1 exists on the interval minus infinity 0. Next, we have to check if the given function is differentiable on 0 infinity. Let x belongs to 0 infinity. The given function f of x equal to mod x. Here x belongs to 0 infinity, then f of x is equal to x. We know that f of x equal to mod x. Here it can be written as minus x on x less than 0, 0 x equal to 0 and x when x greater than 0. This is the definition of modulus function. That is why here x belongs to 0 infinity, that is x greater than 0, f of x is x. Then next we can consider f dash of x is equal to what? Limit h tends to 0, f of x plus h minus f of x divided by h by the definition of differentiability. That is equal to limit h tends to 0. Here f of x plus h. Here f of x is x. Then f of x plus h is x plus h. Then minus f of x is x divided by h. Then here x and minus x cancel. That implies limit h tends to 0, h by h. H by h, it is 1. That implies limit h tends to 0, 1. It is equal to 1. That is, here f dash of x exists, f dash of x equal to 1 when x belongs to 0 infinity. That means what? The given function is differentiable on the given interval. That is, f of x is equal to mod x. It is differentiable on the interval minus infinity 0 and 0 infinity. That implies what? Here f of x equal to mod x is differentiable on minus infinity 0 and 0 infinity. That is, the given function is differentiable both interval. Then next, but it has no derivative at x equal to 0. That is, how can we prove? At the point at x equal to 0, the function has no derivative. That means the function is not differentiable at x equal to 0. How can we consider? Here we have to consider the left side of 0 and right side of 0. That means here we have to find out the left hand derivative at x equal to 0 and the right hand derivative at x equal to 0. If these two derivatives are equal, then we can say the function is differentiable at x equal to 0. Given function is f of x equal to mod x. First, we have to find out the left hand derivative of the function at x equal to 0. That is, it is denoted by LF dash of 0. It is equal to limit h tends to 0, f of 0 minus h minus f of 0 divided by minus h. That is, it is the left side of 0. That is, here we have to find out the left side of 0 it is minus h and the right side it is plus h. Therefore, here the function is f of 0 minus h minus f of 0 divided by the smallest increment minus h. Therefore, L f dash of 0, that is the left hand derivative of f of x at x equal to 0 can be written as limit h tends to 0, f of 0 minus h minus f of 0 divided by minus h. By the definition, f of x equal to mod x. Then substituting here, it is equal to limit h tends to 0, f of 0 minus h, that is mod of 0 minus h minus f of 0, that is mod 0 divided by minus h. That is equal to limit h tends to 0, modulus of 0 minus h is h divided by minus h. Here modulus of 0 means 0. That is equal to limit h tends to 0, h by minus h equal to limit h tends to 0, h by minus h, that is minus 1. That is equal to limit h tends to 0 minus 1. Minus 1 is constant. Therefore, limit h tends to 0 minus 1 is minus 1. That is, the left hand derivative of f of x at x equal to 0 is minus 1. Next, we can consider the right hand derivative of the function f of x at x equal to 0. We have to find out right hand derivative at x equal to 0. That is r f dash of 0. That is the right hand derivative at x equal to 0. It is denoted by r f dash of 0. It is equal to limit h tends to 0, f of 0 plus h. That is the right side of 0. F of 0 plus h minus f of 0 divided by h. Now here, the given function is f of x equal to mod x. Therefore, it can be written as limit h tends to 0. F of 0 plus h can be written as modulus of 0 plus h minus f of 0 is mod 0 divided by h. Now here, limit h tends to 0, modulus of 0 plus h, that is h, then mod 0, the value will be 0, divided by h. That is equal to limit h tends to 0, h by h. It is equal to what? Limit h tends to 0, 1. H by h is equal to 1. That implies limit h tends to 0, 1. 1 is a constant. Therefore, limit h tends to 0, 1. The value will be 1 itself. That is, the right hand derivative at x equal to 0. That is r f dash of 0 is equal to 1. Now here, the left hand derivative at x equal to 0 is minus 1 and the right hand derivative at x equal to 0 is 1. That means what? Here, left hand derivative at x equal to 0 not equal to right hand derivative at x equal to 0. That means what? F of x is not differentiable at x equal to 0. That implies f of x equal to mod x is not differentiable at x equal to 0. That means at a particular point at x equal to 0, the function is differentiable or not. Now here, it is not differentiable because the left hand derivative not equal to right hand derivative. Therefore, the function is not differentiable at x equal to 0. But the function is differentiable on interval minus infinity 0 and 0 infinity. But it is not differentiable at a particular point at x equal to 0. The function is not differentiable because the left hand derivatives and the right hand derivatives are not equal. Therefore, the function is not differentiable. Now here, we have to consider one not. By the theorem, we know that f has derivative at x equal to c, then f is continuous at x equal to c. How can we prove? Let us consider the previous question. F of x equal to mod x. That means f of x equal to what? Minus x when x less than 0, 0, x equal to 0, and x when x greater than 0. Then how can we draw the graph of this function? That is, here we have to consider the function f of x equal to minus x, that is minus x value, that is x less than 0. F of x value is minus x, that is minus x value. The function is minus of minus, that is positive on the second quadrant. That means it is y-axis on the positive y-axis. Therefore, the graph is y equal to mod x when x less than 0, this one. Then at x equal to 0, 0 itself. Therefore, we have to draw this region. That means when x less than 0, what about the derivative of the function? That is y dash is equal to minus 1 existing. Then next, when x greater than 0, then how can we consider this region? That means this one. Here x greater than 0, when x equal to 1, 1, x equal to 2, 2, x equal to 3, 3. Then same manner here, when x equal to minus 1, it is 1. When x equal to minus 2, it is 2. Because x less than 0, f of x is minus x, that is minus of minus 1 plus 1. Here, f of x equal to minus x on the left side, that is f of minus 1 means minus of minus 1, that is plus 1. Then f of minus 2 means minus of minus 2, that is 2. Like that. Therefore, the graph is continuous graph. That means here the derivative of the function on 0 to infinity what? Y dash equal to 1. That is here the function is differentiable and it is also continuous. That is this graph is continuous. At x equal to 0 it is 0. That means the graph is continuous graph and it is also differentiable. That means the graph has no breakpoint. That means the differentiable functions are always continuous. Differentiable functions are always continuous. That is here first notice differentiable functions are always continuous. Then second one, the continuous functions are may or may not be differentiable. How can we prove? Continuous functions are may or may not be differentiable. That means we couldn't say it is always differentiable. How can we prove? We know that f of x equal to mod x. It is continuous at x equal to 0. How can we prove? The function is continuous at x equal to 0. Continuous at x equal to 0 means what? Here we have to prove the left hand limit and right hand limits. First we have to consider the left hand limit. Limit x tends to 0 minus f of x. What is that? Limit x tends to 0 minus f of x is minus x. Less than 0, it is minus x. That implies limit x tends to 0 minus minus x. The value will be 0. Then next we can consider the right hand limit. Limit x tends to 0 plus f of x. What is that? Limit x tends to 0 plus here f of x is x. That implies the value will be 0. Here left hand limit and right hand limits are equal. That means the function is continuous. Here left hand limit equal to right hand limit. That implies f is continuous. But by the previous question, we proved that f of x equal to mod x is not differentiable at x equal to 0. That means the function is continuous at x equal to 0, but it is not differentiable at x equal to 0. That means this function is continuous, but it is not differentiable. That means continuous functions are may or may not be differentiable. That is the continuous functions are may or may not be differentiable. But all differentiable functions are continuous. Consider the question. Consider the function f of x equal to mod x minus 1 plus mod x minus 2. First question, prove that the function is continuous at x equal to 1 and x equal to 2. Here, the given function is what? F of x equal to what? F of x equal to mod x minus 1 plus mod x minus 2. Now here x minus 1 and x minus 2 are polynomial functions. We know that it is continuous. And mod x minus 1, that is a modulus function. Modulus function is also continuous. That is here f of x can be written as the composition of two continuous functions. Let us take g of x equal to mod x, h of x equal to x minus 1 and k of x equal to x minus 2. That is f of x can be expressed as the combination of g of x, h of x and k of x. That is how can we prove? That means f of x equal to mod x minus 1. Mod x minus 1, it can be expressed as g composition h of x. That means f of x can be written as g composition h of x plus then modulus function g of x. That is g composition k of x is x minus 2 polynomial function. That is g composition k of x. We know that composition of two continuous function is again continuous. That is g composition h of x means what? Modulus of x minus 1. Then plus g composition k of x means modulus of x minus 2. It is continuous. Why? Composition of two continuous functions are continuous. That is f of x is continuous. Here f of x is continuous at x equal to 1 and x equal to 2. Next question, show that f is not differentiable at x equal to 1 and x equal to 2. Here first we have to find out f is not differentiable at x equal to 1. That's why first we have to find out left hand derivative of the function f at x equal to 1 and right hand derivative of the function f at x equal to 1. If both are equal, then we can say the function is differentiable at x equal to 1. Now here f of x equal to mod x minus 1 plus mod x minus 2. First we have to find out the left hand derivative of the function at x equal to 1. That is L f dash 1 equal to limit h tends to 0, f of 1 minus h minus f of 1 divided by minus h. That is equal to limit h tends to 0. Here f of 1 minus h. F of x is mod x minus 1 plus mod x minus 2. Therefore, f of 1 minus h equal to modulus of 1 minus h minus 1 plus modulus of 1 minus h minus 2. Then minus of modulus of 1 minus 1 plus modulus of 1 minus 2 divided by minus h. That is equal to limit h tends to 0. 1 and minus 1 cancel. Then mod minus h plus next term modulus of 1 minus h minus 2. 1 minus 2, that is minus 1. Therefore, modulus of minus h minus 1. Then minus of modulus of 1 minus 1, 0 plus modulus of 1 minus 2. That is modulus of minus 1 is 1. Therefore, minus 1 divided by minus h. That is equal to limit h tends to 0. Mod minus h is h. Then modulus of minus h minus 1. That is modulus of minus h minus 1 on the left of 1. That means it is minus of. The function is minus of minus h minus 1. That is equal to h plus 1. Minus into minus plus. Then minus into minus plus. That is h plus 1. Then second term will be h plus 1. Then minus 1 divided by minus h. Here 1 and minus 1 cancel. That is limit h tends to 0. H plus h divided by minus h. That is equal to limit h tends to 0. H plus h, 2h divided by minus h. That is 2 into limit h tends to 0, h by minus h. That is equal to 2 into limit h tends to 0 minus 1. That is equal to 2 into minus 1. That is equal to minus 2. That is the left hand derivative of the function f at x equal to 1 is minus 2. Next we have to prove the right hand derivative of the function f of x at x equal to 1. It is denoted by r f dash of 1. It is equal to limit h tends to 0, f of 1 plus h minus f of 1 divided by h. Now here the given function f of x equal to mod of x minus 1 plus mod of x minus 2. It is equal to limit h tends to 0, f of 1 plus h. Here f of x is mod x minus 1 plus mod x minus 2. Then what is the value of f of 1 plus h? It is equal to modulus of 1 plus h minus 1 plus modulus of 1 plus h minus 2. Then minus of f of 1 is what? Modulus of 1 minus 1. Then minus of f of 1. That is minus of modulus of 1 minus 1 plus modulus of 1 minus 2 divided by h. That is equal to limit h tends to 0. Then modulus of 1 plus h minus 1. Then 1 and minus 1 cancel. That is mod h. Then plus modulus of 1 plus h minus 2. That is modulus of h minus 1. That is 1 minus 2. That is minus 1. Then modulus of h minus 1. Then minus of here modulus of 1 minus 1. That is 0. Plus modulus of 1 minus 2. Then mod minus 1 is 1. That is minus of 1 divided by h. Then it is also equal to limit h tends to 0. Mod h. The value will be h plus modulus of h minus 1. It is also equal to modulus of 1 minus h. That is, mod value has not changed. Modulus of h minus 1 is also equal to modulus of 1 minus h. Therefore, it can be written as 1 minus h, then minus 1 divided by h. Now here, h and minus h cancel. 1 and minus 1 cancel. That is, it is equal to limit h tends to 0, 0 by h. It is equal to 0. That is here. The left-hand derivative of the function f of x at x equal to 1 is L f dash of 1. It is equal to minus 2. And the right-hand derivative of the function f of x at x equal to 1 got r f dash of 1. It is equal to 0. That implies L f dash of 1 not equal to r f dash of 1. That means it implies f of x is not differentiable at x equal to 1. Not differentiable at x equal to 1. Similarly, we can prove that f of x is not differentiable at x equal to